All right. Physics H remote student. So here's a virtual lab you're going to do here. I'll show you the real setup here. We had springs, and we hung masses off of it, and we saw how far the spring stretched as we added masses to it. Now, the purpose of this lab is to determine the relationship between the force applied to the spring and how far it stretches. All right, spring force is what we call it. It's actually really the other way around. It's the force the spring exerts on an object when it is stretched a certain distance. But the force the spring exerts on the mass is equal and opposite to the force of the mass on the spring. So we hang the mass on there. We determine the force it applies. We measure how far the spring stretches from its equilibrium position, and we collect that data in a nice graph here, right? So your columns on your graph, well, that's going to kind of depend here. You're going to do it virtually here using the simulation. And let me move this out of the way so I can see it. You do the lab one here. And you can get to this from the topic, masses and springs, or you can read the title here and get there. So let's bring in the meter stick here. You want to set the meter stick so that it's going to be, what is this, millimeters or centimeters? I don't even know what this is. Let me put 100 grams in here and see what happens. So you want to get it not vibrating, right? So you want to try to grab it when it's at its, pause it once it gets to its peak if it's moving. So we're tracking the end of the spring here. This must be millimeters. Oh no, centimeters. 90 centimeters. So, all right. So when I put 100 grams on there, oh, that's a lot of mass. That's why. Let's get it down. You probably want to go maybe by 20 grams at a, or 20 grams at a time. Let me get it down to, can I type in there? No. Okay. Starts at 50 grams. So, all right. Is that the equilibrium position? I don't even know. Must be. All right. So, it's stretched down. Let me take the mass off for a second. Okay, so there we are. I'm going from the bottom of the spring. Okay, so there's the equilibrium position. Hit the little stop sign. So that's at about, if this is 10 centimeters, we've gone 1, 2, 3, 4, 5, 6, 7, 8 centimeters. So it's 50 grams and 8 centimeters. You need to put this into meters and kilograms, okay? So in kilograms, this is 0.05 kilograms, and this would be, it's 8 centimeters, it's going to be 0.08 meters. Write that down. Then increase the mass by maybe 20 grams. All right, we're up to 70. All right, now it's at about 10, 11 centimeters of stretch length. And you just keep going. So 0.07 kilograms, and you're going to write this information down in a data table now. Actually, I have a pitch over on the board there. So the data table will look like this. Let me write it for you here. It'll be the mass in kilograms. So you're going to have to convert from the grams there to kilograms. All right. And then, oh, look, what's this? These lines. Okay, so that's kind of cool. You can add that to it and move this over here. That's a much nicer way. Mass in kilograms, you're going to convert that to the force applied in newtons. All right. Mass in kilograms, force in newtons. So you're going to multiply all the masses in kilograms by 9.8 to get the force in newtons. And then you're going to measure the stretch length, which is going to be the variable x in centimeters. All right, x in centimeters, and convert that to x in meters. X is the spring stretch length. You convert it to x in meters. So divide those by 100. So you keep increasing the mass. All right. Then we get the next video, which is going to be just put in with this video, and it goes through me plotting the data. So the next video I show how to plot the data. Actually, I guess I'll stop this here, and then we'll talk about what that graph kind of indicates later on. I'll actually make a second video. These two I'm going to splice into one, and then I'll make a second video. So hold on a second, and you can see the data you collected and what it looks like. Now, I will say in this next portion, I wasn't thinking about this first portion at all. So you will have collected all the data. I just read it off my cell phone from what we did in lab. I had taken a picture of a student's data set, which I can try to show you here a little bit. I don't know if this will be visible at all. So their data table ended up looking like that. Yeah, it's not going to focus on that. Their data table ended up looking like that. So 7 data points would be good. And then you're going to graph them as shown in the next video. You're going to graph them, get a fit line, and then we'll talk about the data analysis later. Okay, so good luck to you. Email me if you have any questions. You can use this simulation. All right, so you've collected your data. First thing you want to do is you want to name these columns, okay? Don't be lazy about this part. This makes your life easier in the end. Spring. Now, I know that we controlled the force and measured the length, but I want you to plot these. I want you to plot these this way so that it makes more sense when we do the analysis. So the short name for spring stretch length is an X. So that's convenient. It's already an X. The units should be meters, right? So those centimeters that you measured off the meter stick, you should have converted to meters. For Y, this is going to be the force acting on the spring. I'm just going to call it force, capital F, units, newtons. All right, so I got rid of X and Y column. And if you accidentally called the X force and the Y stretch length, that's okay because we can always switch these in the end. So now I'm going to put the numbers in here. So in meters, this was 0.25. Hit the down arrow, 0.04, 0.05, 0.065, 0.08, 0.09, and 0.1. So it looks like it went up by about a centimeter each with each force. So this first one for the force now is 0.49, 0.686, 0.882, 1.078. A little too many sig figs, but it's not gonna matter in the end. 1.274, 1.47, and 1.666. All right, so we've got an outlier here. We'll see where it is. So once you plot your points, we'll go auto scale from 0. Where is that outlier? Where'd it go? Oh yeah, way over here. What did I type? Did I type something in wrong? Let's see. Oh yeah, look at it. The very first point. It should have been 0.025. So that was my bad. All right, so now I'm going to auto scale from 0. I'm going to put a fit line on it. So there it is. Our y-intercept is pretty low, but unfortunately I do kind of see it. 0.09, 0.1. It's a little under 10% of our total, so I might have to factor this y-intercept in and try to explain what was going on. But overall, there it is, 15.39 newtons per meter. So once you think you have this, all right, with the proper slope, y-intercept, you can call me over. I'll take a look at it and print it. But the slope of the line should have units of newtons per meter. Okay, that's very important. The slope of the line should have newtons per meter. So then we'll look at each of your graphs and compare them to one another and see how the slopes compare. Okay? So I'm going to stop sharing this, and I'm going to come around and check your videos out.